Okay, so we're going to continue where we left off to get the second order Taylor approximation and approximate the cube root of 1.1. So what do we get here? Well, first we have to compute the second order Taylor approximation. So for that, we're going to need some derivatives. And we'll need at least two derivatives to write down the t2, and I'm just going to compute the third derivative because we're going to use this for the error approximation. So recall that the error is dependent on the next derivative. So in particular, f of 1, we're centered at 1, so f of 1 is the cube root of 1 is 1. F prime of 1 is a third. And f double prime of 1 is negative 2/9. And we'll look into the third derivative later. But for now, what can we do here? Let's go ahead and write down the Taylor series, or Taylor polynomial, t2 of x. Let me write it first in its without plugging in anything. F prime of 1, x minus 1, f double prime of 1, x minus 1 squared over 2 factorial. Okay, so this is t2. So this is 1 plus 1/3 times x minus 1. Well, in this case, it's going to be a minus because we have a minus for this second derivative. Minus 2/9 times x minus 1 squared over 2 factorial, which is 2. So these 2's cancel, and we get 1 plus 1/3 x minus 1 minus 1/9 times x minus 1 squared. So this is t2, the second order Taylor approximation. And what we want to do is we want to approximate the square root of 1.1, so we plug in 1.1 into this function. So let's see, what do we get? We get 1 plus 1/3 times 0.1 minus 1/9 times 0.1 squared. And I didn't compute this in advance, probably should have, but let's just do it now. 0.1 divided by 3. So this is 1 plus 0.0333 and forever minus, and then we have 0.1 squared divided by 9, and that's 0.001111, and then 1's go on forever. So if we add that up, we get the following: 1.032222. Okay. So the question is, how accurate is this? This is the part where we computed the Taylor polynomial. Now it's a question of accuracy. So what is the maximum error? Okay, well, for that we need to look into r sub 2 of x, which is the error corresponding to the Taylor polynomial of second degree, and that equals it depends on the next derivative, or the next term in the Taylor series, which is this. And here x is 1.1 because that's what we plugged in, and c is somewhere between a, the center, and the value x 1.1. Now let's look at our third derivative term first. The third derivative term was 1/3 times -2/3 times -5/3 x to the -7/3, right? Sorry, -8/3. I guess 5 and then -1, -8/3. Right? So this is equal to 10/27 times 1/x to the 8/3. So let me just put in a c there just because symbolically that's the letter we've been using. Now, since c, so notice here, since c is greater than or equal to 1, 1 over, well, let's do this stage by stage instead of me directly jumping. That means c to the 8/3 is also greater than or equal to, it'll be 1 to the 8/3, which is also 1. And hence, 1 over c to the 8/3 is less than or equal to 1 over 1. So hence, this term right here, when we're looking at f3 of c in absolute value, this is already positive, so we don't really have to do the absolute value sign, but let's just put it there because usually, in case it's a negative, you still should do that. This thing is less than or equal to 10/27 times 1, which is just 10/27. So first thing you always want to do, this is your m. This is the m, which we used as a symbol when we stated the remainder theorem. So R2 of x in absolute value, it's less than or equal to, remember it originally had this third derivative term, which that third derivative term now is less than or equal to 10/27. So this thing is less than or equal to 10/27 times, and then we had x minus 1 cubed divided by 3 factorial, where now we plug in, so we're plugging in R2 of 1.1. This is less than or equal to 10 divided by 27, and then 1.1 minus 1 is 0.1, so 0.1, I'm just going to ditch the absolute value, everything's positive, 0.1 cubed divided by 3 factorial, which is 6, and if you compute this, you get 0.00006173. So this is the accuracy level. So the the value that we got here, 1.032222, that is within, if you add and subtract this value, the actual cube root of 3. So let me just maybe write that in. So the cube root of 1.1 is within 0.00006173 of our solution, which was 1.032222. 1.032222. Okay. Okay, so that concludes 11.11. In the next video, we will begin chapter 12.